Welcome to this course of Advanced Manufacturing and Process Modeling. So, we are going to start the welding and process modeling. So, we will discuss with the introductions to the welding processes, welding terminologies, and types of joints, classification of welding process, insight of weld metallurgy, etc. So what is basically the joining process? So joining, as we have discussed earlier also while introducing this course, that joining is basically it is basically happening between two members of the parts that are getting assembled together, and it can be of permanent and it can be of temporary nature. So like temporary nature of joints can be achieved by rivets or screws. But here in case of welding, the joint becomes permanent in nature. So in this case, the joining of different elements happens because of the atomistic bonding between the neighboring parts which are getting assembled, and because of the diffusion that happens at atomic scale. So based on the nature of the joining process, it can be classified as autogeneous, homogeneous and heterogeneous. So autogeneous welding, so in this case for joining no filler metal is added from outside, and in case of homogeneous welding, basically we use the filler metal as of same composition to that metal which is used for from the metal pieces which are getting welded. So for example, if you just consider the case of a butt welding, so assume this is butt welding. We will discuss about explain what is called butt welding. So for now, so assume that this is the piece A and this is the specimen B, and then we are basically joining them by fusion welding technique. So when we will call it as autogeneous and homogeneous and heterogeneous. So when we are not adding any filler material from outside, and this weld bead, this position is called basically as the weld bead, that is getting formed from the contribution of the material A and B. That means fusion, melting of material A and B causes this bead formation. So then we will name it as autogeneous welding process. And when when we are adding filler metal externally, so assume this is the electrode. So if this filler metal is of same material, that means if A and B are of equal material, then this is the material C, that is the filler material is also of same composition with A and B, then we call it as homogeneous welding. Okay. There are some examples of homogeneous welding are gas and thermit welding. And what is called heterogeneous welding? When the filler material C is not equal in composition with the parent metal, that is A or B. That means A is equal to B, not equal to C. So this is the case of heterogeneous welding. So filler material different from the parent material. The example is soldering and brazing. We will learn about these welding processes in detail later on. And so the joining processes can be classified based on their joining technique. So mechanical bonding, it can be achieved by, so these are also temporary joints. It can be achieved with screw and screw elements, fasteners, and also it can be classified as temporary and semi-temporary or semi-permanent. So semi-permanent joint can be further classified as the rivet joint, stitches, staples and shrink fits. And solid state the atomistic level bonding between the adjoining geometries or parts or plates can be classified. Where atomic level bonding happens can be classified as solid state welding, liquid state, that is fusion welding, and solid liquid state or semi solid state welding. Then they can be further classified or grouped into several welding processes. For example, if we start with the solid state welding processes, it can be further classified as cold welding, friction welding, diffusion welding and hot forge welding. And then where cold welding can be further classified as pressure welding, ultrasonic welding and explosive welding, and whereas fusion welding can be classified based on the source, I mean heat source, as chemical when we are using chemical heat source, then we can call it as chemical fusion welding, and when we are using electric current, then we can call it as electric welding, which can be further classified as arc welding, induction welding and also the resistance welding based on the nature and the nature and type of the electricity we are using. And so we are classifying this electric welding into 3 categories, whereas chemical welding we can classify as gas welding and thermite welding. And then solid liquid state or semi solid state welding can be classified as brazing, soldering and adhesive bonding. So, we will discuss into all these processes individually and we will go into the detail, but before that we will try to learn about the fundamental principles of welding processes. So, welding is basically a materials joining technique which produces coalescence of materials by heating them to suitable temperatures with or without the application of pressure or by the application of pressure alone. I mean, in that case there is no heat source is used for fusion, like for example the cases of solid state welding, where I mean pressure is basically responsible for heat generation at the interface and diffusion at the interface, and thereby the joining, I mean atomistic level bonding and diffusion between the adjoining, I mean metal parts happens. So, this it can happen with or without filler material, like we have discussed earlier. So, when we use filler material, we classify it as homo or heterogeneous welding. When we do not use filler material, we call it as autogeneous welding. So, welding is basically used for making permanent joints. It is used in the manufacture of automotive bodies, aircraft frames, railway wagons. So, welding is everywhere. So, like there is widespread application of casting being the primary manufacturing process, either for developing net shape parts or for developing preforms for subsequent manufacturing processes, and similarly welding finds its application in all kind of industries as a well established joining technique, because none of the assembly parts can be developed as a whole. Although after the advent of additive manufacturing, there is we can nullify the assemblies to a great extent, and we can develop the adjoining parts in the form of a single part by additive route, but still I mean welding has its several application, because I mean additive is not suitable until now for very large parts, or it is not economical as well to nullify I mean all the joints being utilized by several industries. So, yes, welding is still very versatile and it is very much widely used I mean manufacturing technique or forming route. So, the advantages are welded joint has high strength, sometimes it is having higher strength than the parent metal itself. It depends based on what kind of filler metal is being used and what are the welding conditions, what are the microstructures that are getting generated at the weld joint. Number 2 is different materials can be welded. Welding can be performed any place, no need enough clearance. They give smooth appearance and simplicity in design. They can be done in any shape and any direction, and they can be automated of course, and they provide a complete rigid joint, and addition and modification of existing structures are also quite easy. And but of course there are some disadvantages. What are they? So, the members may become distorted due to uneven heating and cooling during welding process, because it is a localized phenomena. Unlike casting, it is a, you can consider it as a local casting within a large mold. We will going to we will discuss that in detail later on. And number 2 is their permanent joint. To dismantle, we have to break the weld, and they also deals with the high initial investment. So, you basically cannot alter the joint once it is done. So, that is a I mean, so that is why you need to be sure before welding that you do not want to dismantle or alter the assembly later on. and also I mean you need to design to avoid for the distortion it causes because of the differential cooling rate at different sections of the I mean assembly. Okay. So, now we will discuss about the welding terminologies, I mean different sections of the I mean welding welded geometry. So, I mean so the number 1 is backing. So, it is the material support provided at the root side of a weld to aid in the control of penetration. So, again if I draw a typical example of butt weld. So, again this is plate A and this is plate B and we are achieving a single V butt joint. So, then if we provide a plate at the base of the these two adjoining plates which are going to be joined by butt welding technique. So, this is basically the backing that can be provided to achieve the desired weld in a proper manner. And number 2 is the base metal. So, base metal, the metal to be joined or cut is termed as the base metal. So, here A and B are the base metal, and then number 3 is the weld bead or the so bead is the metal added during a single pass of welding. So, here this is the weld bead. So, assume so this is basically the cross sectional view that is shown over here, and from here you can understand the weld bead which is the bead appears as a separate material from the base material, but it is a separate material truly when we are talking about heterogeneous welding, and when we are not referring to the heterogeneous welding process, then it can also be generated from having same composition with that of the base metals which are experiencing the joining process. And then number 3 is crater. So, it is basically the in arc welding electric, it is one of the one kind of electric welding. A crater is the depression in the weld metal pool at the point where the arc strikes the base metal plate. So, for example, you have a electrode, you are doing arc welding. So, then this is the arc generated. So, it creates a depression over the workpiece material. So, that is called basically as referred as crater. Okay. And then deposition rate, it is the rate at which the weld metal is deposited per unit time, which is termed as deposition rate, which can be often expressed as kg per hour. And then fillet weld, so the metal fused into the corner of a joint made of two pieces. So, a typical example of fillet weld for a two plates A and B again, which are placed perpendicular to each other and a joint is made. So, this is a typical example of fillet weld. Okay. So, the metal fused in the corner of a joint made of two pieces placed at approximately 90 degrees to each other. So, the included angle theta here is 90 degree. Okay. So, with this we will move into the penetration. So, penetration is the depth up to which the weld metal combines with the base metal as measured from the top surface of the joint. So, again for simplicity I am again drawing a butt joint, single V butt joint. Okay. So, this is basically the weld bead that is formed, and assume that up to this the generated weld bead, it basically the weld metal combines with the base metal, that is A and B. So, then this is basically from the top surface. So, this is the penetration or the dilation region of the weld bead that is formed at the top of the geometries which are experiencing welding. And then puddle, so the proportion of the weld joint that melted by the heat of welding is called puddle. So, root, it is the point at which the two pieces to be joined together is nearest. So, this is basically the root section of the weld joint. Okay. So, and then the track weld. So, before achieving the complete welding, so basically we initially deposit. So, if you consider this is the case, so here up to this it can be done in a single pass, which is called track welding, and then after that the whole bead can be done at subsequent one or two passes or in some cases based on the desired thickness it can be even more than that. So, this initial bead is called the track weld, which is responsible for keeping these workpieces, I mean the base metals together. So that they do not get dislodged from that position where they need to get welded, otherwise it can cause distortion and also defects, and the assembly may face may fail to meet the dimensional requirements, and it can lead to the rejection of the assembly as well. So, so this is the track weld, and then the toe of the weld. So, it is the junction between the weld face and the base metal. So, again if we are taking the example of the fillet weld where the workpieces are placed perpendicular to each other. So, this is your typical weld bead, this is the case of a fillet weld. So, in this case when the so the toe of the weld is the junction between the weld face. So, this is the weld face and base metal. So, this is the toe of the weld, this is the toe of the weld. Okay. And then torch. So, torch in case of gas welding we are talking about torch like fuel which mixes like oxyacetylene torch. So, the torch mixes fuel and oxygen and it controls delivery of the fuel and the oxygen, that means the ratio of the fuel and the oxygen, which also determines the flame temperature and the flame geometry as well as the flame color. So, these are the welding torch, and then the weld face. So, it is the exposed surface of the weld. So, this is basically the weld face WF, and then weld metal, the metal that is solidified at the joint is called the weld metal. So, the metal which is solidified in this weld bead is called as weld metal. And then so the weld pass, a single movement of the welding torch or electrode along the length of the joint which results in a bead is a weld pass. So, this is weld pass, and then as we are taking the example of butt joint often. So, again we are going to discuss about the butt joint. So, it is between the two pieces of metal are placed edge to edge in the same plane and welded. So, this is a typical example of butt joint. So, what is the difference between butt and lap joint? So, butt joint, when the two pieces are placed at along their edges and the based on requirement the groove can be of separate types. So, this is a case of V groove, single V groove butt joint. So, there can be cases where we can go for double V groove butt joint. So, this is a typical example of double V's where this is the so here this is the groove 1 and this is the groove 2. So, double V butt joint. So, which is largely different from lap joint, where lap joint is not happens between the edges, rather it happens between the surfaces. So, this is a case of lap joint LW, and this is a case of butt joint BW, which is single groove. So, only one groove, and this is a two groove butt joint. Okay. So, based on the nature of the groove, like bevel shaped groove, so then we call it as a bevel butt joint, then V groove butt joint that I have drawn over here, and double V groove butt joint, then J groove butt joint if the groove is appeared to be the shape of the English letter J. And then when U groove butt joint, when we are making the groove in the form of a U, not as a V, then we call it as U groove butt joint. Okay. So the advantages of butt joints are very much common in pipelines, structural components and pressure vessels. So, we are talking about edge to edge joining in the same plane, and the advantages are simple preparation technique suitable for automation. The variants are we have discussed already. Based on the groove geometry we can classify butt joint. And now coming into the lap joint, in this case the two metal pieces are where overlap happens along the surface are welded along the edges of the overlap. So, then we call it as lap joint. Applications: sheet metal industries and resistance welding. So, the advantages are increased surface area for welding and high strength, increased surface area for welding and high strength. Variants are single lap joint and double lap joint. So, so here this is a typical example when it is welded along the I mean one edge, so then it is a case of single lap joint, but here it is welded along two faces, so then it is a case of double lap joint. Okay. So T joint, so what is T joint basically? So T joint is a special case of, I mean fillet weld. So in case of fillet weld, we have discussed earlier that when the workpiece A and workpiece B, workpiece A and workpiece B are placed at perpendicular to each other, then the joint we produce are called as fillet weld, FW. And when we are placing the the plate vertically at the middle of the bottom plate, say the plate A is placed vertically and there is a included angle of 90° on both the sides, and then the weld is formed. That means, so it is basically double fillet weld. It is a case where we are getting a T joint because the joint looks like the English letter T. Okay. So the applications are many, like structural components, stiffeners, frames, etc. And the advantages are simple setup, high load bearing capacity. Challenges are this kind of joints are very much prone to residual stresses. And then the case of edge joint. So this is basically a typical example of edge joint, when the edges of two plates are aligned and welded, often with a small overlap. So the applications are thin plates, sheet metals, tanks, pressure vessels, etc. The challenges in case of edge joint are so it is having low strength compared to other joints and limited use for thick plates. Okay. And then the case of corner joint, it is quite similar with the I mean fillet weld. So you can see the two pieces are joined at a right angle to form an L shape. So this is because this is very much similar to the English letter L. So that is why it is a corner joint is termed as the L joint also. Applications are frames, box constructions, sheet metal structures, etc. And the variants are closed corner joint, open corner joint and fillet corner joint. Based on the joint made along at the corner, it can be classified by these three variants. And then fillet joint, it is a triangular weld which is applied to the intersection of two surfaces. It is very much common in lap, corner and T joints. So the applications are, so these are all basically fillet joints, like we have discussed in case of corner joint, and then earlier we have discussed this fillet joint in case of achieving T joint and edge joint. So these are the classifications of the joint based on their shape or the appearance of the joint. Okay. So the applications of fillet, I mean this kind of fillet joints are general structural weldings and pipelines. It is very much economical and also does not require much edge preparation. So welding can also be classified based on the heat source or the energy source. So when we are basically using the thermal energy for welding, then we can classify the welding primarily as gas welding, where the example is oxyacetylene welding, and then arc welding. Arc welding I mean can be classified as metal inert gas welding or MIG, tungsten inert gas welding, or TIG. I mean also as submerged arc welding, shielded metal arc welding, so on. And then the resistance welding, when we are basically utilizing the electrical resistance, the heat generated by the electrical resistance, that is spot welding and resistance seam welding. Okay. So this is the classification of welding techniques based on the energy source that is going to be utilized for welding purposes, and then based on the mechanical energy, I mean when we are classifying the welding techniques based on the mechanical energy. So friction or mechanical pressure which generates heat. The examples are friction welding. So when heat is generated by the friction between two adjacent surfaces, so then we can achieve the friction welding. And then ultrasonic welding, where it uses high frequency vibrations to generate heat. So I mean so then so these are the classification. And then when the energy source is chemical in nature, so then the heat is generated from chemical reactions. The examples are thermite welding, when basically we use aluminum and Fe3O4 which reacts each other, and it is serves as an exothermic reaction, and then I mean it can generate the heat which is responsible for fusion welding between the adjacent I mean plates or the parts, and then explosive welding also, where a controlled explosions are utilized to achieve fusions between the adjoining plates, and thereby we can achieve diffusion and atomistic level bonding among them, and we can weld them in that way. And then so after chemical we move to the electrical energy, and electrical energy, based on the electrical energy, the welding can be classified as electric arc welding and resistance welding, and so, and also induction based welding, but primarily the difference is basically the arc welding and the resistance welding. So based on the state of the matter, the welding can be classified as fusion welding when we are talking about transforming or developing a liquid pool in the joint between two adjoining geometries, then we term the process as fusion welding. So the examples are arc welding like TIG, metal inert gas welding, tungsten inert gas welding, submerged metal arc welding, etc., and also gas welding like oxyacetylene welding, laser beam welding, electron beam welding. All these are classifications or subparts of the fusion welding processes. And then when we move to the solid state welding processes, so then in this case the materials are joined without melting at the adjoining locations, or without forming the typical weld pool. We can achieve solid state welding by applying pressure and heat. So examples are friction welding, and also cold welding, diffusion welding, and ultrasonic welding, and liquid solid state welding. So when involves partial melting of materials, that means so it is also can be called as semi solid welding. Like we generally use this kind of technique for low melting filler materials. So like brazing, soldering, most of you might have seen in the your home, TV, the electronic circuits, they are primarily repaired by brazing or soldering route. Mostly you must have seen the soldering torch, that is generally so this is a technique which is using a semi solid slurry. So that is why it is deals with the partial melting of materials. And then there is adhesive bonding, where we basically achieve the bonding between two neighboring plates with the help of applying adhesives at the interface, and also by applying pressure. So until now we have discussed about all the classifications of the welding processes, and which is summarized in this slide. So like classification criteria can be energy source, and the resultant classifications are these, and then classification criteria can be material state. However, we classification in terms of heat source is also discussed earlier. However, we are still we are discussing for the classification of the welding processes based on process mechanism and mode of welding for the first time here. So based on process mechanism, the welding techniques can be classified as manual, semi-automatic, and automatic, whereas based on mode of welding, it can be classified as pressure assisted or no pressure assisted welding, and the applications are widespread, starting from automotive, it can be applied to mining, electrical, defense, and so on, several industries. Okay. So so the principles of solid phase welding, that we can, the solid state welding processes may be carried out both at the room temperature and at an elevated temperature, without of course melting any part of the following adjoining surfaces. So for a better understanding of the quality of a solid phase joint, it is worthwhile to recapitulate the strength and cohesion of metals. So a defect free crystal fails by a cleavage along its crystallographic plane, where the interatomic force is the weakest. So as a result, two new surfaces are produced, and the surface energy gamma surface energy gamma is defined as the work done to create these surfaces. So here in this case, the strength of a single crystal sigma c can be expressed as sigma c is equal to root over E, that is Young modulus or the modulus of elasticity, into gamma by D, that D is the lattice spacing in the cleavage plane, and surface energy is as gamma, that is told earlier also. So, in case of a brittle solid, the failure takes place by the extension of the cracks already present within the material, and the bulk strength is much reduced from that given by the above equation. So, the bulk strength sigma b can be expressed as sigma b is equal to root over E gamma by L. So, in this case again it is very much similar to the previous equation. So, E is the Young modulus, gamma is the surface energy, and L is the characteristic length. So, here in the solid phase welding processes, the 4 important factors are surface deformation, surface films, recrystallization and diffusion. So, these are the 4 primary mechanism which governs the solid state or solid phase welding processes. So, in case of pressure welding, the bulk deformation is used as an index of the surface deformation and is expressed based on this equation. So, as T I minus T F by T I. So, T I are the initial and final thicknesses into 100%, and also in case of circular specimens it can be defined as the initial and the final diameters. So, so that is D F, the final diameter square, minus D I square by D F square into 100. So, is as so the bulk deformation is used as an index of the surface deformation, and they can be expressed like this when we are talking about circular specimens and when we are talking about sheets, sheet specimens. Okay. So, so now so when we have discussed the solid state welding, we will briefly discuss the principles of fusion welding or liquid state welding. So, in case of fusion welding process, the material around the joint is melted in both the parts to be joined. So, the fusion welding process, as I told earlier, that it can be autogenous or homogeneous, and metallurgically there are 3 distinct zones. So, again if I take the example of a single V butt joint, so which is shown over here. So, you can see, so the 3 zones here, it is basically the fusion zone where you can see the weld bead formation, and then so the fusion zone encompasses this one. Okay. So, I am terming it as fusion zone FZ, and then there is the heat affected zone, which is a zone immediately analogous to the fusion zone, which is termed at heat affected zone HAZ, and then there is the unaffected original part or the base metal. So, these are the 3 zones that is unique to the fusion welding processes. So, the most important factors governing a fusion welding process are the characteristics of the heat source, the nature of deposition of the filler material in the fusion zone known as the weld pool, the heat flow characteristics in the joint, and the gas metal or slag metal interactions or reactions in the fusion zone, and the cooling of the fusion zone with the associated contraction, residual stresses and metallurgical changes. So, all these things play their individual roles, so that which basically determines or defines the microstructure and properties of the fusion welded joints. So, like we have already discussed about the variants of fusion welding based on heat source, like there are several heat source like electric source, chemical source, and then also the thermal source, and also exothermic chemical reaction like thermit welding, and then there is also electric resistance heating. So, these are the several heat sources which are generally used for fusion welding processes. So, we will discuss in detail about different fusion welding processes in the next class. So, today we are stopping here. So, for today goodbye to all of you, and we will meet again with the discussions on the different fusion welding processes. Thank you.